Hello, I'm Mike, and this is...
I'm Tamas.
And you're watching Soft Magnetics
Hard Topics.
So what are we going to talk about today, Tamas? Let's say common mode chokes or any mode chokes in shield beads. So we hear that term get used around a lot. You'll see even on our website, some parts are called shield beads. Some are called chokes. In application, they'll be called beads or chokes, or the name gets moved around a lot, and I guess it could probably be used interchangeably. But as somebody that builds a lot of chokes and everything, what is the distinction in your mind? How do you delineate between those two terms?
Look, the shield beads technically also kind of inductors, also chokes, but they are very discrete, very small components. Mainly, you have one turn inside. In extreme cases, 1, 2, maximum 3 turns, and the Fair-Rite core. And it is also a choke, but it is a very small one. You can check on our website; they are in the millimeter ranges, and this their size will give a big limitation on their usage. So I would say rated current wise or rated voltage wise, if you want to build a circuit for rated current 1000 volts, the chip build, if you have a common mode chip build, then you just simply don't have enough safety distance between the lines. So it's not necessarily not a very good choice for that. And also, if you need a circuit where its current carrying capacity 20, 40, 60 amps, then chip build might be too small for that. So they are really very good discrete components, but let's call it power range. In the lower power range, it can be used. If you need something bigger, then you most probably need a choke, classically named choke. And the point there, it is the chokes. There are off-shell chokes, but they're technically are very flexible because you can design your own one. You can pick a core with the proper geometry. You can design the winding on it, and all together, if you combine the winding with the core, you can have your desired parameters. And it's mainly custom made. It's in one hand a very good thing. So if you make a custom choke, most probably you can solve your problem, and technically all your imagination limits what kind of choke you do, and probably cost efficiency as well. But if you this is the main thing behind. So it's very flexible, gives you flexibility how to deal with the problems.
And you say chokes, and shield beads, I guess, for that matter too. But often you see the word common mode ahead of a choke, so it's a common mode choke. But common mode and differential mode EMI are both problems kind of solved by similar solutions. Well, I guess differential mode is not going to be attenuated by a common mode choke so much, but a common mode choke can go backwards on that one.
Yeah, common mode chokes also have a differential mode in
right.
So it makes sense. So what is a common mode choke and a differential mode choke? Basically, a differential mode choke, let me say, when the current is running in a normal way from the higher potential to the lower potential, or from plus to minus, then it will run in a loop, right? And it's differential mode. And the differential mode choke has 2 connecting points, 2 outlets. And basically, due to this, they have one winding, right? Because one winding had a beginning and end. In a common mode choke, you need minimum 2 windings, so you will have minimum 4 connecting points. And what you do with the common mode choke, the problem with the common mode disturbance is that it's not running as the normal current, but in the 2 lines. For example, if you have a DC system with the positive bar and the negative bus bar, and the common mode current or common mode disturbance will go in the same way and attack the load at the end, and they will find, because every disturbance wants to return to the source, and they will find a common way, usually via the grounding to the source. And the problem with this that it can cause you a lot of issues. It can cause you EMI issues. It can blow up your Y capacitor. In low frequency applications, it can damage your motor or whatever. So what you do? How do you do a common mode choke? Simply you take a core, typically a ring core or toroid, and you orientate design the winding on the way that when normal differential mode current is running, the flux induced by the two windings will cancel each other in the core. So theoretically, the circuit does not see any impedance, just the DC resistance. To be very accurate, and I just mentioned that the common mode chokes also have differential mode inductance. In reality, you will have a stray inductance.
Yeah, leakage between the...
Yeah, if you work from the field of transformers, you use the freeze leakage. If you are from chokes, then you say stray inductance. And this will give you, depends on the design, it can be the differential mode inductance is in the range of 1%, 0.5% of the common mode. It can go up to even 2-3, but those are special designs. So what you do with that when you have the normal current, it's mainly the impedance of the common mode choke is very low, so it does not cause big troubles for the circuit. But when a common mode disturbance comes, then the windings start to work together, not against each other, and this will give you a quite big inductance, and it will help you to suppress, to choke these certain frequency components or whatever you want to do with that.
I guess maybe kind of an interesting way to look at, chokes versus shield bead is almost, I guess the way I kind of rationalize the shield bead in a shield bead or a bead, ferrite bead type of application, the ferrite's doing most of the lifting, right? So that's what's providing you your insertion loss and everything. But on a choke, it's a combination of, the actual core, whatever you're using, ferrite, or it could be some other material. But importantly, and probably most importantly, the winding architecture. Maybe that's like a good distinction between them. The bead is the component. The winding, augments that a little bit, but maybe we're just, on a choke, it's nothing without the winding.
That is absolutely correct. So shortly, the main difference between the bead and the choke is the winding. So.
Yeah. So I guess on that topic, when we're trying to we're trying to build a choke, what do we look at in terms of a material? How do you decide when ferrite's the right option, when it's nanocrystalline, when it's a powder iron core, silicon steel, whatever?
So let's talk about common mode chokes. The first, and I think the most important step, the most important is always to understand what's the problem, what you want to solve. And first you need to identify or determine what frequency range, what is the frequency range where you want to use your device. This will give you the kind of itinerary, kind of indication what ferrite material will you use, or if you are even not necessarily ferrite, so based on the frequency you can even decide to go with something else. But let's talk about ferrites.
Yeah, we're supposed to do that, but yeah.
Ferrite can be, or usually is a very cost-effective solution, and I like so if you are in a very special case and have to solve a very special problem, then you might need special shapes.
Mm-hmm.
And probably ferrite is the only high permeability ferromagnetic material, but you can build any shape from that technically.
Yeah, there's limitations practically at some points, but you can get see a part back there pretty massive. You can make some really large and really small parts.
Of course, if you want to be cost effective, you have to make compromises. But turning back to the selection topic, first you need to know the frequency range where will you operate, and of course depends on the application. If it's a common mode choke, then it's most important frequency. When it's a power application, you need to pay extra attention on the losses and the frequency.
Mm-hmm.
And the second topic what I always have to consider is the temperature, because ferrite itself is a kind of temperature sensitive material. There is a very critical temperature for all ferrites, so-called the Curie temperature. Above that point, the material will lose its ferromagnetic properties. Thanks God, when it cools down below that again, it comes back. So it's a reversible thing.
Yeah, and it's important to look at some of the charts for the materials too, because you're gonna, not only does it just stop at some point, but it moves below that point.
So the rated parameters that you see in catalogs mainly taken at room temperature, what is 27, 23
25.
Celsius or something like that. Depends. I saw values at 20, 23, and 25, but let's say room temperature. But you will see a different performance of your chalk or different feature properties of the ferrite at 85 degrees, 100 degrees. And if you have an application where the ambient temperature is 70 degrees or 85 degrees, then most probably your core will never operate under room temperature conditions, right?
Yep.
This is just one thing. And the other thing is also there might be some self-heating of the core itself when it's being used. Depends on the application more or less. And third, and also very important point, the winding. The winding itself will have a self-heating. And since you fit tightly on your core to have a good coupling, there are also other methods, but just take in consideration that you tightly wind it on your core for good magnetic coupling, then a lot of heat, but from the self-heating of the winding will be somehow absorbed by the ferrite, so you will heat up your core. And just for example, if you have an application with ambient temperature of 85 degrees, that is a typical value, and you have a self-heating of your winding, I don't know, 30 degrees, then you can assume that your core might have around 100 Celsius degrees under normal operating conditions. And at 100 Celsius degrees, you will see different inductance value or different permeability, different saturation characteristic. And it is the third topic that we just arrived at. Based on the inductance and all the geometry, you will have flux density in your core. And you must pay attention on the BH curve of the core. Don't drive it into saturation, because if you drive it into saturation, it will just not work properly.
Right. Oh, I think that's a pretty good basic primer without it becoming a lecture course. So, thanks for tuning in. Hope to see you soon in the next video on soft magnetics.
Hard topics.
Have a good one.